Let's look at how we would find a resultant vector if we were given two vectors, we'd say maybe a force or something like that, two different force vectors pulling in different directions, and we would have to find what the resultant vector is. Now what the resultant vector is it's an equivalent vector if you were to replace both of the forces that are pulling in a particular, in opposite directions, if you were to replace that with just one force that does the same thing, that's what the resultant vector is. So let's take a situation where we've got some sort of a box or something, right? And we're pulling that box upwards with a particular force here of, we'll say 5 newtons. And also something is pulling it horizontally this way with a force, we'll say, of 7 newtons, so slightly larger. So how could we replace these two forces with one force that does the same job? Essentially, this box, we'll say, is going to move, it's going to accelerate off in this direction somehow because it's being pulled upwards and over to the right. So it's going to move off, it's going to accelerate in this direction some way. And I would want to say, well, how could I replace this with one single force instead of two different forces that makes the box accelerate off the exact same way, as if there's no difference. So let's just draw the vectors on their own out here. We've got a 5 Newton vector here. We've got a 7 Newton one, is a little bit longer, 7 Newton vector on this side. And so in order to find the resultant vector, we have to use the parallelogram law. So we have to complete this parallelogram. In other words, we take something that's parallel and has the same length as this vector, parallel to that vector, and has the same length. So we can kind of draw that in the dashed way. It kind of looks the same thing, like that. And then we have something that's parallel to this line and has the same length. So we can draw that in like this. And where they meet, well, that's where the resultant vector ends up. Okay, so your resultant vector will look something like that. And what we need to work out is, we call this v for the length of this vector. We need to figure out what v is, and we also have to figure out what theta is here, this angle to the horizontal. So in order to figure out, we know that this is a 5 Newton force upwards, so that's at 90 degrees. We know that this is a 7 Newton force with a 0 degree angle to the x-axis. So here we have to figure out, well, what's the magnitude of v here, and also what's the angle that it makes with the x-axis. Okay, how do we approach this? Well, we start first by recognizing that this vector is the same length as this vector, and because they're parallel, we can say that this has, this has a magnitude, we'd say, of 5. Okay, so it has a length of 5 or 5 newtons here. In other words, it's almost like you kind of take this vector and place it over here, and so you can make a right angle triangle now, because we said this was at right angles, so this must be at right angles here. So we've now got a right angle triangle. We can draw that out on its own just to show it more clearly. So over here now we've got a right angle triangle. Here are the lengths. We've got 7, we just call it 7 for now. We won't bother with newtons. We'll just say it's got a length of 7 on that side. It's got a length of 5 on this side, and we don't know what the length of this is. We're going to call it v. There's our right angle triangle, and there is our angle theta, and we have to figure out what theta is. Okay, let's start with the length of v, or the magnitude of v. Well, the way that you would write that is v with 2 bars either side of it like that, so that it shows this is the magnitude of v. The magnitude of v then, how do we calculate that? Well, we've got a right angle triangle here, and the v is the hypotenuse. So I've got the hypotenuse here, and I've got the other 2 sides, so I can use Pythagoras, right? Now, you wouldn't have to write by Pythagoras. By Pythagoras, you could work this out by doing the hypotenuse squared, that's v squared, is equal to the other 2 sides squared and added. So 7 squared plus 5 squared, like that. So v squared is equal to, that's 49 plus 25. So v squared is equal to, that's 60, 74. And so v is equal to the square root of 74. Get out a calculator. And you get 8.60 for that. 8.60. 8.60 newtons, because this is a force. So now we know that the length of this is 8.6. That's fine. Now we need to get the angle. So let's work out the angle for this. We'll do this in a different color so that it's more clear. We're working out this angle theta. Now we could put this 8.6 in here. We could say, well, this is 8.6, this V, so we now have 7, 5, and 8.6 for the different sides of the triangle. But let's avoid that in case we've made some sort of a mistake in calculating the length of the hypotenuse. It looks sensible and it looks right because 8.6 is longer than any of the other two sides and the hypotenuse is the longest side. So that would make sense. I mean, if the answer to this came out at 4.2 or something, then you would know you were definitely wrong. But let's look at how we could calculate theta without using this, just to keep ourselves away from any errors. Well, this is theta, so the angle opposite this, the one that's, or the length, sorry, that's opposite this angle is 5. So 5 is the opposite side from the angle here, from the angle theta in this right angle triangle. And 7 here is the adjacent. So I've got the opposite and the adjacent, and using trigonometry, tan gets you the opposite and the adjacent. Tan theta is equal to the opposite over the adjacent. So because I've got the opposite and the adjacent, I can solve this. Tan theta is equal to 5 over 7. Tan theta is equal to, we get a calculator to do 5 over 7. That works as a 0.7143. Okay, big issue here with most students is getting theta on its own now. Right. Okay, so theta is, we've got a tan of theta here, we've got a function operating on theta, tan, right? In order to get rid of that function, we would have to use the inverse function. This is kind of multiplying, this is kind of like multiplying 1 over x by x in order to get rid of all the x terms. We want to get rid of this tan, so that's a tan function, so we would have to use an inverse tan function on that in order to just get theta back out on its own, right? But if we're going to do inverse tan on this side, well, we have to do inverse tan on this as well. And that's how we, essentially what happens here is this cancels and you just kind of end up with theta on its own. That's not very good mathematically, but it kind of explains what happens. Using an inverse tan function on a tan function to basically let it cancel off. And so you have to use the inverse tan function on this side as well. Okay, so let's get rid of those bits out of my way. So let's do this so that we just get theta is equal to the tan inverse of 0.7143. So we do the tan inverse of that on a calculator. And you should know how to do this from maths class, I hope. And for that I get theta is equal to 35.54 degrees. So we've described what the resultant vector is here. In other words, if I took this box and I applied these two forces like this, horizontally and vertically, it would be the same as if I had another box sitting beside this, just pulling at 35.54 degrees from the x, from horizontal, with a force of 8.6 newtons. And I would find that both of those boxes would move exactly the same. They would accelerate the same and everything. I couldn't tell them apart. So that's how you find a resultant vector of two other vectors.